this video, I will introduce the BAC-SNN, a deep spiking neural network with adaptive feedback and balanced excitatory and inhibitory neurons. Spiking neural network transmit information through discrete spikes that perform well in processing spatial temporal information owing to their non-differential characteristic difficulties possessed in designing SNNs that deliver good performance. SNNs trained with backpropagation have recently exhibit impressive performance by using a gradient approximation. However, their performance on complex tasks remains significantly inferior to that of deep neural networks. The human brain perceives and learns under the coordination of multi-scale statistic learning rules. We should learn from the learning methods of the human brain from multiple perspectives, such as the structure and the function, so as to improve the performance of the current spiking neural networks. In addition to the traditional model of information transmission in the brain, the presynaptic neurons emit spikes along the axons to the postsynaptic neurons. In particular, the ATAPs connects the soma to a self-feedback loop that transmits information to itself. As shown in the figure, the ATAPs in the brain act on the memory potential to help regulate the spikes, friction, and network activity in a time-delayed self-feedback. Inspired by the ATAPs in the brain, they introduced an adaptive feedback mechanism for convolutional spiking neural networks. To reflect the modeling of the delay, we use spikes fired at the previous time step to regulate the input to the neurons. Both excitatory and inhibitory neurons exist in the brain. Their balanced combination helps with learning and inference. As shown in the figure, the excitatory neurons exhibit excitatory postsynaptic potential, which makes it easier for the postsynaptic neurons to fire. By contrast, inhibitory neurons exhibit inhibitory postsynaptic potential, making postsynaptic neurons less likely to fire. We define excitatory neurons as neurons that release positive spikes, and inhibitory neurons as neurons that release negative spikes to simplify their modeling. Combining the above two mechanisms, they implement a spiking neural network, a BAC-SN based on adaptive feedback and balance of excitatory and inhibitory neurons. The results of experiments on several commonly used datasets verify the performance of our BAC-SN. It achieves the state-of-the-art performance on MNIST, NMNIST, and fashion MNIST datasets and deliver impressive performance on the CIFAR-10 dataset while using a relatively light structure. In addition, we randomly select 5 samples from the CIFAR-10 test dataset. We visualize the spikes of the output layer for them. The figure shows that with the introduction of the self-feedback module and the balanced excitatory and inhibitory module, the spikes of the output layer are relatively accurate and stable. However, for the network without these two models, the spikes of the output layer change significantly. This shows that the introduction of the two modules help control the stability of the network and the precious release of the spikes. We have re-implemented the algorithm based on BrainCog and integrate in the base neuron backend node and provide the as you can see the backend node. If you want to use the feedback, you set the if back true, and if you want to use the inhibitory balance, you set the EI true, and we provide the corresponding training codes. In example, you are welcome to contact us if you have any questions. So, very thanks.